Hello, everyone. Today we'll explore a scheme for sending signals faster than the speed of light using entanglement. Let's consider n independent qubits, all in the same state, and look at the likelihood of measurement outcomes. If the state of each of the qubits is ket 0, then 100% of the measurement outcomes will be 0. And similarly, if the state is ket 1, then 100% of the measurement outcomes will be 1. However, if the state is an equal superposition of ket 0 and ket 1, then it's 50-50. 50% of the measurement outcomes will be 0, and the other 50% will be 1. If we have ket 0 or ket 1, but first apply the Hadamard gate on either, that will transform the kets into a linear combination of ket 0 and ket 1. So again, we're in the 50-50 case. On the other hand, if we apply a Hadamard on a balanced superposition state, then it will render it into a single ket. So we find ourselves back in the situation where 100% of the measurement outcomes are all the same, 0 or 1. Here we have two qubits on planet Earth. One belongs to Alice and one to Bob. We let them interact so their states become entangled. And then Bob leaves with his qubit and moves to a planet 50 million light years away. Alice will get some information about what she's doing to her qubit to reach Bob faster than the speed of light using a scheme represented by this quantum circuit diagram, using the power of entanglement between their two qubits. It starts with Alice and Bob's qubit each being in state ket 0. In the first part of the circuit, which takes place on Earth, entanglement is created between them, and the total state of the two qubits is transformed from ket 00 to a superposition of ket 00 and ket 11. In the second part, which also takes place on Earth, only Alice's qubit, which we call the pink qubit, gets operated on. Bob's qubit, which we will call the blue qubit, is left alone. But in the third and final part, which takes place in the faraway planet, only the blue qubit gets operated on. In the next few slides, we'll focus on these last two parts of the circuit. There are two steps to what Alice does to her qubit. In step 1, she either applies a Hadamard on the pink qubit or not. And in step 2, she measures the pink qubit. Notice that the box representing the Hadamard has an h raised to the power s. When s equals 0, the Hadamard becomes the identity, which is equivalent to it not being applied. But when h is raised to the power 1, then that corresponds to the Hadamard being applied. In the first case, the total state stays the same, and the possible states for the blue qubit after the pink one is measured are not superposition states, but ket 0 and ket 1. However, when the Hadamard is applied, the possible states for the blue qubit are superposition states, which it gets projected onto after the pink qubit is measured. Next, in the final part of the circuit, which takes place on the faraway planet, using a cloning machine, Bob makes 2n copies of his projected state, measures half of them, and the other half measures only after a Hadamard is applied on each qubit. Note that the circuit diagram you're looking at is a compact form for this. We'll go back to our compact form. There are two scenarios to consider here. If Alice had not applied a Hadamard on her qubit, this means that the blue qubits are not in a superposition state. So the measurement outcomes for the first group are all identical, while the measurement outcomes for the second group are random. Half of the time they're 0, and the other half they're 1. This is exactly the opposite of the case when Alice had applied a Hadamard on the pink qubit. Now the outcomes for the first group are random, and the second group identical. In other words, Bob is able to determine the value of S by just looking at the statistics of outcomes for the two different groups, when Alice is so far away. So he's getting this information at a speed faster than the speed of light. This sounds great, But unfortunately, this scheme does not work because a cloning device that allows Bob to make as many copies of his unknown projected state as he likes cannot exist, as you'll show in this exercise. Here, you look at the case where n equals 2. There's a qubit inside the device, which is represented by operator A, in state ket 0. If the input state is ket 0, the device spits out ket 0, 0. If it's ket 1, it spits out ket 1, 1. Take the arbitrary 1-qubit state ket phi and work out both sides of this equation. A ket phi tensor ket 0 equals ket phi tensor ket phi. Are the two sides the same? Au revoir!